devastation in Puerto Rico crippled communications inside and outside of the island. Whether it's emergency traffic or health and welfare, accurate communication is always key. Warren County Technical School students and members of the 721st Mechanized Contest Battalion, Amateur Radio Club, Abbie and Tucker, realized nothing beats the speed and accuracy of text messaging. Their project, which is called an Emergency Solar Powered Digipeater, created a portable, self-sustaining packet radio digipeater that can be rapidly deployed. Briefly, Tucker is 17 and he's a senior electronics student at Warren County Technical High School in New Jersey. He's a ham radio operator, KD2 JPM. He was originally licensed in October of 2015 and he recently upgraded to general. Good. He is already an associate certified electronics technician and he's not even at a high school. Pretty amazing. He's a member of several radio clubs and his goal is to pursue electronics technology as a career path and hobby. As a Boy Scout, he earned the Radio Merit Badge and is working towards his Eagle. My brother's an Eagle, so go for it. And then Abigail Tucker is also a radio amateur, KD2PUA. She's 16 and currently a third-year student at Warren County Technical School. She earned her amateur radio license this year and is a proud member of the radio club. In her free time, look out, she trains in kickboxing and Brazilian Jiu-Jitsu. Don't mess with her. Okay, without further ado, let's welcome Emma.
Good morning, and it's an absolute privilege always for me to be working with young people, but it's especially an honor to present them at certain forums. And this one is high up on my list. At Dayton, where these two young people, as RCA Young Achievers, already have given a presentation that wowed the audience, I then invited them to come here. I told them ahead of time at Dayton, don't be nervous because you are in front of 200 people in the audience, but I have dubbed the Dayton Hamvention audience as the love audience. Because when you're up here and you're 16 or 17 years old, you feel the support that comes from that group. And I have put the RCA Technical Symposium in that same category. So you've got my personal thanks for all the support that always gets shown toward the young presenters that we be here. And always please keep in mind, the demographic we're dealing with here is high school and below. So I just think it's fabulous that they are getting up in front of these kinds of audiences and sharing their expertise, which they have. So somebody a lot smarter than I am, Abraham Lincoln, once said, if you want to be able to predict some of the future, take an active part in creating it. And I believe that's what all of us in this room and RCA Youth Activities are doing. So my personal thanks to all of you, and I'd like to introduce three people to you. Beside Abbie and Tucker, Bob Rochesk, KA2PBT. You want to wave, Bob? Bob has been a ham radio friend of mine for decades. Bob's passion, besides being a computer and networking engineer in the telecom sector, is in inspiring and coaching young people. And he is responsible, he and his team, for bringing many, many young people into different kinds of forums, including Dayton and the Technical Symposium. So personal thanks to you, Bob. And without further ado, I know you're going to love this. Here is Abbie and Tucker.
Both of you together. Thank you. 1, 2, 3, cheese. One more. 1, 2, 3. Thank you.
Hi, I'm Tucker Dunham. I am from Warren County, New Jersey. I go to Warren County Technical School. I participate in the electronics program. I'm a senior, and I was a presenter at the Dayton Youth Forum this past May. I recently attained my Eagle Scout rank in Boy Scouts, and I'm a second place state champion in the New Jersey Scouts USA vocational competition.
Hello everyone, I am Abbie Heim. I am a junior at Warren County Technical School, and I am the electronics program like Tucker. I am a newly licensed ham, and I, in my free time, like to train in kickboxing and Brazilian Jiu-Jitsu. So, ago after Hurricane Maria, most communication systems were offline. And up here we have a map of Puerto Rico, and it depicts the cell phone outages after Hurricane Maria. The darker colors are what shows complete outages. According to the FCC, after the storm, 90% of cell sites were inoperable. People in the disaster area traveled for miles to find the few working cell sites and to get word to loved ones outside of the affected area. The situation in Puerto Rico was so dire that during the recovery period, the ARRL, in cooperation with the American Red Cross, assembled a team of volunteer amateur radio operators who traveled to Puerto Rico to assist in providing communications. So during the emergencies, passing accurate information in a timely fashion is critical. And emergency personnel may need to find shelter for a displaced family or request a medical assistance to coordinate search and rescue operations. Finding locations for food and water distribution and simply reuniting separated families are also very important. At times like this, ham operators are called on their ability to make use in less than ideal situations. So for hams, activities like field day, summits on the air, parks on the air, and others are good to prepare for operating under difficult conditions and are prepared for sustained loss in resources such as commercial power going out. When roads and ports have been damaged, even fuel or emergency generators become scarce. So we wanted to build something that could support communication efforts in the most extreme conditions. And so we thought to ourselves, what could be the most extreme situation than space? So communication satellites must be self-sustaining and reliable, and satellites can easily be refueled or repaired, if at all. So they're typically small and light because of the challenges of putting a payload into orbit. Here is a picture of some more inspiration. So after brainstorming, we decided what we wanted our requirements to be. It had to be constructed from easily obtainable parts. We needed to be able to easily assemble it. It needed to be self-sustaining as far as power was concerned, and the design had to be simple, as well as it needed to work under various conditions and perform additional tasks if needed. It also needed to be easily transported and stored. And lastly, we needed to be able to afford it. Our solution is a solar-powered digital repeater or digipeater to relay digital messages. It is powered by batteries and solar cells to run indefinitely. It is small enough to be transported by a single person, as you saw Tucker brought it up himself, and it is designed to be placed on a hill or tall building. So, in our daily lives, texting and email has become super common with us, and it is a part of our daily communication. And sending a text message is a lot quicker and more accurate than having other means of communication, such as a phone call, and texting doesn't require active participation from all parties simultaneously, like direct verbal communication does. So there are many digital modes used by amateur community, and we needed to pick one. For a little while, our idea was to use mesh networking using repurposed Wi-Fi equipment, and it's become very popular recently because it uses microwave frequencies, and range can be limited by obstructions like building in trees, and alignment tends to be critical, so that ended to be quite a downside for mesh networking. While amateur mesh networks could have impressive speeds, a slower speed mode could be used to communicate the important who, what, and where necessary in an emergency. So we decided that we were going to go with a 1200 baud AX.25 on VHF, commonly known as packet radio. So now I know what you're thinking. Packet radio is old. We're past that. But the thing is, it's old and reliable. Even though only around 1200 baud is kind of slow compared to network speeds today, it doesn't really need to be fast because it's simple, reliable, and high-speed data isn't necessary for an emergency situation. So packet radio is an amateur radio technology from the early 80s, and it sends data between computers. The protocol AX.25 was based on the commercial X.25 data switching protocol. The data is organized in frames or packets and is transmitted in bursts. Error checking is done on the entire frame. Bad frames are discarded and reset. Frames are tagged with a source and destination IDs, so only the messages intended to you are the ones that you see. There are two transmission modes: connected mode, which is considered most reliable and reception is guaranteed in the order that it is sent. And connected mode would be used in cases where a message must be delivered accurately in its entirety. There is also an unconnected mode, where a packet is unreliable or best effort. Unconnected mode is typically used for sensor data like weather instruments or position information where a missed packet is not critical and you can just wait for the next report. So, digipeating is a method of relaying packets to extended range. Unlike conventional voice repeaters, packet repeaters are simplex half-duplex, which means they use a single frequency to store and forward the packet. A digipeater will passively listen to a channel, and when it hears data, it will receive the packet, error check it. If it is error-free, it will transmit it back to the same channel. The packet can be routed through multiple digipeaters, further extending the range. So, for our digipeater, we are using a Raspberry Pi with TNC board that allows packet capability. For power, we are using solar panels providing energy to the Raspberry Pi and the radio, and float charts to the batteries. Here is a quick explanation in video form of what the communication would look like. find the one spot where the sun's shining through and direct all the panels that way. And here we have our two-piece J-pole. Everything is hidden right inside of it. Plug it right in at the top. The connector goes right through, and it's a pretty seamless design. Thank you, Tucker.
Thank you. Several of the pieces were printed, 3D printed for the project. Most notably was the solar panel mounts. There were 36 parts printed total just to hold the solar panels. The parts first needed to be constructed using computer-aided design, also known as CAD. We used SketchUp mostly because it is popular and it is free for commercial use. For 3D printing is a rapid manufacturing process where material is heated and extruded to robotically produce a 3D part. The 3D printer used is the Creality CR10. It is an inexpensive and reliable piece of equipment that has a large build area, and we were able to print several pieces at once. The printing material, also known as filament, is sold on 1 kilogram spools at a cost of around $30 per spool. For what we were doing, a single spool could produce hundreds of parts. Solar panel mounts are designed to allow the user to easily install and replace solar panels. The design is minimal and requires only 1 bolt to assemble. 2 pieces snap together to hold the panel that is then bolted to a 3rd piece which is attached to the body. A bracket to hold the radio was printed as well as a bracket to hold the Raspberry Pi. Top and bottom caps were also printed. The top cap has provisions for the antenna mount and connector. The bottom cap contains a standard thread to accept a broom or painter's pole. Several containers were considered for design, including Pelican boxes or ammo cans. We eventually decided to go with a 4-inch PVC pipe because it is easy to source, cheap, easy to work with, and can be made weather resistant. It is also a good form to mount the solar panels on. The solar panel mounts are attached to the PVC pipe with a large hose clamp, allowing them to be rotated around during cloudy days. During the day, solar panels power the radio and the Raspberry Pi, as well as charge the batteries. When the sun goes down, the batteries keep everything running. The power conditioning system consisted of 3 separate voltage converters. The first voltage converter, which is a buck boost converter that is wired directly to the solar panels, steps down the voltage from the solar panels to 14 volts to charge the batteries during the day and provide power to the other converters. The second converter is a buck converter that steps 13.8 volts down to the 7.6 volts required by the radio. That is then converted by a 3rd converter to 5 volts for a Raspberry Pi. Sealed lead acid batteries, also known as SLA, were chosen for their ease of use. SLA batteries are easier to charge with simple circuitry and much more forgiving in overcharged and undercharged conditions. The solar panels we purchased were spec'd at 5 volts at 500 milliamps, but actual performance fell far short. We originally expected to use 6 solar panels, but doubled that to 12 to make up for performance shortcomings and give it a little more headroom on cloudy days. We arranged the panels in a series parallel configuration to provide 15 volts at 2,000 milliamps, or 30 watts. The popular Raspberry Pi single-board microcomputer was chosen as the brains of the system. The Pi is a full-featured Linux computer that costs around $35. It runs the popular open-source operating system known as Linux and has several general-purpose input-output ports that can be used for expansion. The TNC Pi is a terminal node controller that attaches directly to the headers of the Raspberry Pi. The TNC Pi modulates and demodulates audio tones into data and sends frames to and from the Raspberry Pi. The Linux operating system on the Raspberry Pi processes the data frames into packets. Packets can either be repeated or processed by the program. By taking advantage of the Raspberry Pi's onboard Wi-Fi adapter, we can configure the Pi as a wireless access point. Using a computer or a smartphone, we can access the platform wirelessly and as a communications endpoint or manage the device. Originally, we selected an inexpensive Chinese radio with the intent to keep the unit as cost-effective as possible. But soon, we ran into several problems. After hours of testing and troubleshooting, we determined that the poorly designed radio was distorting the incoming data and signal, making decoding sporadic. Additionally, the TNC Pi works best with the squelch open, but in this mode, the radio refused to transmit. After finding an economical, better engineered radio, we built a new interface cable and tested the new radio's capabilities. With a new receiver that was designed under higher quality control, the data was transmitted and received perfectly clear. We needed to build an interface cable to connect the radio to the TNC Pi to get the AFSK audio to the modem. It can be seen on the slide. To summarize, our solution is a portable, self-sufficient, solar-powered digimeter. We wanted to use the Raspberry Pi for its ease of access and modification, switching regulators for the sake of efficiency, and 3D printed parts for the ability to be easily recreated. Our final design was compact. All the electronics fit into a 4-inch PVC pipe. Starting from the bottom, you see two 6-volt SLA batteries. Above that is the power management circuits to charge and maintain the batteries. Above that is a Raspberry Pi with the TNC Pi hat attached to the top of it. And finally, on top of that is a 2-meter handy-talkie. With each section created with perf board, cut circles, and using screws as standoffs, the internal assembly can be easily removed for maintenance or adjustment. Here's what the project looks like in its deployed and stowed state. Here's a short video.
So, after we finished, we realized that we built an expandable platform that could be used for many other things, such as an APRS node, a weather node, and a packet endpoint. With a PL259 connector, we can put a variety of different antennas to fit the system. The Raspberry Pi lends itself to an endless expandability with the addition of software and sensors. A special thanks to Carol Berry for the opportunity to present, to Kaylin Diploma Trophy for his guidance in completing the project, to Robert Shesk to being such a lovely mentor, and for Mr. Bob Oppen for his contribution of the antenna material and his guidance. Excuse me. And of course, to all the members of the 721st Mechanized Contest Battalion. Thank you.
Okay, so we had a very nice presentation from these two young people. Now we'd like to take some questions. I have one first, which is the mechanical stability. Have you thought about the issue of the thing blowing over? Do you have some kind of a base plate that you've thought about?
I have thought about that, and what we can do is we can take a painter's pole, and that painter's pole can be inserted into the ground to provide stability for the project, to prevent it from falling over due to winds.
Next question.
So I'd like to first thank Abbie and Tucker for,
Stand up, please.
I'd like to thank Abbie and Tucker for an excellent presentation. I think this was really great.
Thank you.
How much power did the transceiver you have run? And without charging the battery, what kind of life expectancy would you get out of the equipment if you weren't charging the battery?
Great question. I don't exactly, I apologize, I don't remember the exact current draw from the whole system itself. But as I was testing it, I was able to run it for 3 days indefinitely without the batteries going below about 12 volts. Any other questions? Yes, sir.
The project there is an excellent project, easily deployable. One question though is the devices that would communicate with it. They're not exactly universally available. I don't even know where my Commodore 64 is. Do you know if there's perhaps a cell phone app that can do AX25 that you could just plug into your handheld and use that?
Yes, I can use my cell phone and I can access this when it's on wirelessly because this transmits a Wi-Fi access point, and I can modify it or send digital messages out or receive them.
It was by Wi-Fi.
Yes.
Okay, because I was thinking